Welcome to lecture number 10 from Modern Control Theory. In this lecture, we will be considering the application of Cayley-Hamilton theorem for the calculation of inverse of a matrix and state transition matrix. So, according to Cayley-Hamilton theorem, a square matrix satisfies its own characteristic equation. This is the statement for Cayley-Hamilton theorem. So what does it mean? Actually, characteristic equation, as you know, or polynomial in terms of lambda, it is p lambda equal to the determinant of a minus lambda equal to 0. Why I is considered? Because lambda is a scalar quantity and we have to have a minus a matrix. So we should multiply lambda by identity matrix I. So getting determinant of this, we would be finding an expression in terms of this polynomial lambda. If it is 2 by 2, then lambda square plus some constant lambda plus some constant. If it is nth order, lambda raised to n plus some constant lambda raised to n minus 1 plus some constant lambda raised to n minus 2 plus some constant plus some constant equal to 0. But according to Cayley-Hamilton theorem, what is it is a square matrix satisfy its own characteristic equation. So it does mean p in terms of a function in terms of a equal to 0. That is, here it was p in terms of lambda. So what it stands for, that we should simply replace lambda by a, and your expression would be becoming like this: a raised to n plus some constant a raised to n minus 1 plus some constant a raised to n minus 2 plus some constant plus so on. And lastly, it would be a constant quantity equal to 0. But here one thing, that it is in terms of a in left hand side, therefore this 0 would be a null matrix of the order of system matrix A, undoubtedly. Now, so initially we have to have the information whether your system satisfies or verify the Cayley-Hamilton theorem or not before proceeding to determination of inverse of a matrix or state transition matrix of a matrix of that system. So according to statement, we have to calculate the value of determinant a minus lambda equal to 0. So from here, lambda 1 for this system, here we are considering this system, so it's lambda 1 and lambda 2 can be calculated by this characteristic equation. So ultimately this is the characteristic equation in terms of lambda, but your Cayley-Hamilton theorem is meant for a square matrix A, therefore it is in terms of a square plus 3a plus 2i equal to 0. So this is the characteristic polynomial of the system for considering Cayley-Hamilton verification. So what it is, it states that the square matrix satisfy its characteristic equation itself. What does it mean? The value of LHS of this expression, characteristic equation, should be equal to value of RHS. So here lambda square plus 3a plus 2i should be equal to a null matrix. If it is so, then system matrix A, defining the system, would verify the Cayley-Hamilton theorem or comply with the conditions of Cayley-Hamilton theorem. And you can proceed for calculation of inverse or state transition matrix. Otherwise not at all. Okay, so we should verify a square plus 3a plus 2i equal to 0 or not. By considering LHS, putting the value of I and a in this expression in this way and solving it, we will be getting a null matrix, which is the requirement of Cayley-Hamilton theorem. So in this way you can say that this system, which was having elements 0, 1, minus 2, minus 3, satisfies or verifies Cayley-Hamilton theorem. Once the statement is proven for a system, you can proceed to calculation of the inverse of matrix. Otherwise not. It is the specific condition. Because what actually otherwise not, for the calculation of inverse of matrix, it is again using the characteristic polynomial of the matrix. So you have to simply multiply A inverse in LHS term and RHS term. RHS is 0. Therefore, A inverse into the polynomial a square plus 3a plus 2i should be equal to 0. Now, on expression, one thing, a square is written as a into a inverse. And here you can say that a into a inverse, this is one of the identity of matrix, property of matrices. So using this property, if you are multiplying a matrix to its inverse, it is always an identity matrix. And if you are multiplying identity matrix to a matrix, then it is equal to that matrix only. So A into A inverse would be converted to I. So here it is A into I plus 3 into I plus 2A inverse equal to 0. So one thing, then see, if you observe this expression, I is known to you, A is known to you, A inverse can be calculated. So 2A inverse equal to this one, and in this way you are able to determine the value of A inverse very much easily. Now, what about a state transition matrix? For a state transition matrix, initially we should develop the theory. If a function f and its characteristic equation is delta, then that function divided by the characteristic equation is equal to some quantity of fraction plus some remainder over that characteristic equation, because characteristic equation is always or either may be equal to or may be less than of the order of the system. So in this way you can get, if in terms of eigenvalues, it is function f lambda over delta lambda equal to q lambda plus r lambda over delta lambda, or f lambda equal to q lambda delta lambda plus r lambda. F lambda equal to r lambda, say delta lambda for the systems which are satisfying or verifying Cayley-Hamilton, delta lambda equal to 0. Delta lambda, that is characteristic polynomial, that is equal to 0. So this term would become 0. F lambda equal to R lambda would be there, and this, or in terms of A, it is Fa equal to Ra. So, and this would be equal to F naught plus alpha 1 A plus alpha 2 A square plus alpha something, and this expression resembles e की power at expression. So state transition, which is state transition, so state transition matrix can be calculated by Fa, which is equal to remainder Ra. So initially what you have to have, you should calculate the values of the eigenvalues of the system. If you are having second order system, 2 eigenvalues would be there, namely lambda 1, lambda 2. If it is the third order system, you would be getting 3 eigenvalues of the system, lambda 1, lambda 2, lambda 3. So if you are having second order system and you are getting 2 eigenvalues, lambda 1 and lambda 2, then the expression would be equal to F lambda equal to alpha net naught plus alpha 1 lambda 1. So this is alpha naught plus alpha 1 lambda 1 e की power, for second eigenvalue it is e की power lambda 2 t equal to alpha naught plus alpha 1 lambda 2. So one thing that should be cleared, that you are having 2 eigenvalues which can be calculated from the determinant of A minus lambda equal to 0. 2 variables alpha naught and alpha 1, these are unknown. 2 algebraic equations you are having, so it is easy to calculate the value of alpha naught and alpha 1. And in this way, by putting this one, you would be able to determine state transition matrix. Now you can understand by taking an example. A equal to 0, 1, minus 2, minus 3. Its eigenvalues are lambda 1 equal to minus 1, lambda 2 equal to minus 2. Right? So you are having second order system and 2 eigenvalues you got by calculating determinant of A minus lambda equal to 0. So now use the expression, that is F lambda equal to e की power lambda t equal to alpha naught plus alpha 1 lambda. So for lambda 1 equal to minus 1, e की power minus t equal to alpha naught minus alpha 1. Similarly for lambda 2 equal to minus 2, you would be getting e की power minus 2t equal to alpha naught minus 2 alpha 1. See, 2 expressions are there and 2 variables are there, alpha naught and alpha 1. You would be able to calculate the value of these unknown quantities. So by calculating this one, alpha 1 is calculated and its value is this one. Alpha naught is calculated and its value is this one. So in this way you got 2 variable values, 2 constant values, that is alpha 1 and alpha 2. Now by state transition matrix expression, it is e की power at equal to alpha naught I plus alpha 1 a. Put the value of I, a, alpha 1, alpha naught. All are known to you. By putting and solving further, you will be getting the state transition matrix e की power at by this expression. So ultimately what you observe, that you have missed the step of Laplace inverse. Sometimes may be cumbersome to calculate inverse of the system. Here it is not needed to determine Laplace inverse. Directly in terms of t, you are getting the answer. This example was for the roots which are distinct, -1 and -2. If your roots are repeated, in that case, what would happen? What procedure you would be following? Because you would be getting the same eigenvalue. For same eigenvalue, you would be getting the same polynomial, characteristic polynomial. If it is so, how you would be able to determine or solve that single polynomial expression for two unknown quantities? So here, this is one of the example I have searched for, which is having repeated roots. So its roots are lambda equal to -1, -1, repeated. If it is so, your polynomial would be having one value, that is this one, alpha naught plus alpha 1 lambda 1. This is same for lambda 2 equal to -1 as well. If it is so, then how you will be calculating the value of alpha naught and alpha 1? If alpha naught alpha 1 cannot be solved, your expression will not be solved. So for calculating for lambda 1 equal to -1, you use this expression, you ultimately got this expression for another value of lambda, which is as equal to -1. But here you have to have the derivation and differentiation of this expression, both sides with respect to lambda. If it is so, this is the constant value, so its differentiation will be equal to 0. T e की power minus t, because lambda equal to -1 equal to alpha 1. So you got alpha 1 and alpha naught minus alpha 1 equal to this one. So ultimately you can calculate the value of alpha naught. So alpha naught equal to this one, and alpha 1 was known to you, t into e की power minus t. Two variables or two constant values are known to you. Now you can put the value of these one in e की power at, which is the state transition matrix phi t equal to alpha naught I plus alpha 1 a equal to alpha naught into identity matrix alpha 1 into system matrix A. Just solve and you will be getting finally the expression for e की power at in terms of matrix elements. Right? So it is your state transition matrix, how you have calculated using the concept of Cayley-Hamilton theorem. So initially you have to have the verification of Cayley-Hamilton theorem for that system. Otherwise, you can't follow the steps. These are the references. Thanks.